Hello again. In this video, we're going to talk about the difference between intramolecular forces and intermolecular forces. If you haven't already watched it, make sure you go back and watch the video on bonding in solids. We talked about the different ways to make a solid. We had the ionic bonding, covalent network, metallic, and then we had molecular covalent, which uses the intermolecular forces. So this kind of builds off of that. So make sure you understand it first. Well, on the screen here we can see I made a short list here of some of the major differences between intra and inter. The covalent bond holding a molecule together is called an intra. So the prefix intra, you might have learned in English class, means connecting internally or joining within. So if you imagine a boundary around something, the thing that holds it together inside that boundary would be an intra force or intra connection. Like your skeleton. Your skeleton is an intramuscular connection inside the boundary of your body. You probably have heard intra used in things such as intravenous fluids. Like if you're dehydrated, you have to have liquids added. They're added internally, so that's intravenous. Intramural sports. If you have a sibling or a parent who's talked about playing ball in college, but not like Texas versus Texas A&M, but like one fraternity versus the other, those are intramolecular or intramural sports because they're all within the boundary of the school. And we could make more examples like that. On the other hand, if you have an attraction between two different molecules, those attractions are intermolecular. The prefix inter means connecting externally or connecting across a boundary. Such as when, for example, when our football team plays Wiley or Prosper or someone like that, those are two different schools playing, so those are intermural sports between different schools. The highway system that we have in this country is called the interstate highway because those highways originally were designed to cross state lines. So that's your boundary that you're crossing or you're connecting. So intra means connecting within, inter means connecting externally. Intermolecular forces are the ones responsible for your covalent molecular compounds or molecular covalent in order to make those become a solid. They are much weaker than the intramolecular forces. When you take a substance and you try to, a covalent molecular substance now, and you try to make a phase change, you are breaking intermolecular attractions, the ones that are connecting on the outside. You're not breaking covalent bonds when I boil water. You're only breaking the hydrogen bonds, which are a type of intermolecular. And then if you go the other direction and you try to condense steam, for example, you are allowing the intermolecular forces to form and bring the particles at least closer together. So that's the main difference, just speaking in terms of definition. Take a look at this diagram. I think this will help a lot. I know it helped me a lot because words are sometimes hard to picture. That might be one of the most ignorant things I've ever said, but whatever. At least here with this diagram we can visualize what I just got through saying. I have HCl, hydrogen chloride. This is a molecular covalent compound because it's nonmetals, it's not in a covalent network lattice, it's discrete molecules. And this is a polar compound. We've learned recently how to tell the difference between polar and nonpolar. Because this is polar, HCl has a partial negative charge centered around the chlorine because it's more electronegative, and then the hydrogen atom would be partially positive. So we have a polar molecule, positive on the left, negative on the right. Each one of these HCl molecules has the same polarity breakdown. That's a permanent, what we call a permanent dipole. The hydrogen and the chlorine within each of these molecules is an intramolecular force, I-N-T-R-A, intramolecular. It's connecting within the boundary of the molecule. It's holding it together. This particular intramolecular force is a covalent bond, and it's very strong. Now, because these molecules are polar, the partially positive hydrogen of one molecule will be electrostatically attracted to the partial negative of a second hydrogen chloride molecule. So that, represented by the dotted line here, this electrostatic attraction is what we would call an intermolecular, connecting externally. It is a much weaker attraction. So if I have a cool temperature here, I might actually be able to liquefy this gas as the intermolecular attractions build up. But if I raise the temperature, cause the particles to move faster with more kinetic energy, I will first break these intermolecular attractions and then go into the gas phase. Eventually, if I kept adding more and more and more energy, at some point down the line, we could break the covalent bonds. But that would be a chemical change, and we would see things like color changes, etc., etc. All right, so that's conceptually the big difference. Let's bring it home with just one more flow chart. Okay, in this flow chart, I'm kind of summarizing everything I just said about comparing intra and inter. There are three types of intramolecular forces, and I kind of have them ranked from strongest at the top to weakest toward the bottom. All the way down this entire diagram, it's that way. The three types of intra are ionic, covalent, and metallic. All of these can form lattices, as we learned about in the previous video. And these are all very strong. I have ionic on top just because on average it's a little stronger than covalent, because the covalent, as I mentioned before, has two types, the covalent network and the molecular covalent. The covalent network stuff is really strong and is probably stronger than ionic, but the molecular covalent tends to be much weaker. So on average, I would say covalent's a little weaker than ionic, but at times it can be even stronger. That's not super important to put those number one and number two. Metallic is almost always the third of these, but a metallic is still really strong. So if you're connected in a lattice through intramolecular forces, you have very strong connections. And anything with these lattices would have high melting, high boiling points, and be usually pretty hard. They don't have to be hard, some metals aren't very hard, but that's typical. Now, if you're molecular covalent, you can have intermolecular forces, and they can be dominant. The ionic covalent network and metallic, their intramolecular forces and intermolecular forces are about the same thing. So we just pretty much say that those substances don't really have to worry about intermolecular forces. But if you're covalent molecular, your intermolecular forces are very important. Notice here, they're only about 15% as strong as intramolecular. That's a big drop-off, and that's some of the stronger of the intermolecular forces, like hydrogen bonding. London dispersion forces are much, much weaker than the 15%. So we can see there are four of them. Ion dipole, which only occurs in mixtures, so this would be like something polar covalent and then an ionic compound mixed together. And then we have what we call the van der Waals forces. If you're non-polar, London dispersion forces are all that you will have. Excuse me. London dispersion forces are pretty weak, but they can accumulate quickly. We'll talk about that in a LDF specific video. If you're polar, you can have dipole-dipole, and if you're polar with hydrogen bonded, there's a possibility you could have hydrogen bondings, which are even stronger, and we'll talk about why in a hydrogen bonding video. But that's the difference between intra and inter, and notice that inter is much weaker than intra.